forward. Okay, so today we are sticking with the geometry, but we're venturing into the latter sections of geometry, so what you would learn in the end of the second semester. The two things we're going to focus on are trig and circles. So the first thing for trig is the basic memorization of what are the trigonometric ratios. The most common memory device is SOHCAHTOA. If you don't like that one, you basically have to come up with your own. Sometimes people come up with a sentence for it. But the trig ratios tell us that the sine is equal to the opposite over the hypotenuse, and we brushed on this last lesson, but we're going to spend more time on it today. The cosine is equal to the adjacent over the hypotenuse, and the tangent is equal to the opposite over the adjacent. And if you're interested in...
Excuse me?
Yes?
I think the sound is off.
Oh no, thank you. Arr. Wow, that was harder to turn on than it should have been. Is it working now?
Yeah, thank you.
Excellent. I am so glad you said something. So, we were saying we're working with geometry again today, but we're working with the end of the semester, last semester of geometry, working with the trig and with circles. So for trigonometry, find a way to memorize it, but the three trig ratios that we work with are the sine, cosine, and tangent. And the memory device SOHCAHTOA tells us that the sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is opposite over adjacent. So the first thing to use trigonometry is to be able to just memorize this is what we're doing. But the other vital, important piece of information is that you have to identify what is opposite, adjacent, and hypotenuse. Without having those relationships, it doesn't do us much good to have the formulas. So the one that I consider the easiest to remember is the hypotenuse. Not necessarily how to spell hypotenuse, it's kind of annoying and very Greek, but the hypotenuse is constant. Hypotenuse is always the longest side. It's always the one across from the right angle. Some people say that it's the slanting one. We have our right angle 90 degrees, and then the hypotenuse is the one that is across from that. But the hypotenuse doesn't change. It's always that longest side. For our next, opposite and adjacent, opposite and adjacent are reference words. It's not an absolute. So it's similar to right or left. What is right depends on your perspective. For me, right is this direction. But for you guys, that's left. And so it depends on which way you're facing. Opposite and adjacent are also dependent on reference. Opposite what? Adjacent to what? And so they need an angle, usually marked with this circle with a line through it called theta. It's the default symbol for angle. But they need that angle as a reference point. Opposite without opposite something doesn't mean anything. It's gotta be compared to something. And so you need to know which angle you are working with before you try to work with this. Hello, come on in. Maybe I need to. So now that we have this angle, this is the one we're talking about, opposite is all the way across from that angle. Opposite means directly across from. so this would be our opposite side. Adjacent means right next to or attached. We are adjacent to this classroom, or we are adjacent to that classroom. It's the one that's right next door and attached. So when we look at this angle, I'm gonna switch colors for a second. There are two sides that are adjacent to the angle. But one of them's already the hypotenuse. One of them's already taken. And adjacent actually is shorthand for adjacent leg. And so when we're talking about adjacent, it's never going to be that hypotenuse. It's always going to be this side that is also attached to the right angle. And so that's something that gets lost in the shuffle. We tend to abbreviate it just a little bit too much. Adjacent is an adjacent leg. It still has to be the side that's attached to the right triangle. The hypotenuse is always itself. It's always the hypotenuse. So, if I give you this triangle and tell you it's a right triangle, I'm going to label it with R3, 4, 5 because, again, that is a set of numbers that makes a perfect right triangle, and they're nice and easy to work with, so the ACT really likes it. So again, sine does not exist in a vacuum. It has to be the sine of something. In this case, I'm going to say it's the sine of this angle right here with the corner A. The sine of A is going to be opposite over hypotenuse. And so, again, over hypotenuse, hypotenuse comes second as we name this relationship, but I always identify the hypotenuse first. Which one of these sides is our hypotenuse? The 3, the 4, or the 5? The 5. And some people just put an H next to it for their reference. That is our hypotenuse, so we're going to have over 5 for our answer. So sine is opposite over hypotenuse. What is opposite our angle A? 4. Yeah. It's across the way, opposite angle, versus 3 is attached to it. And so our sine of A is 4 over 5. Something that's a little bit different is when you do these in school or you deal with these as problems, frequently you're going to be doing something like the sine of 52 and you plug it into your calculator and you get a big long decimal, right? In general, for the ACT, almost everything they do with sine, cosine, and tangent gets left in the fraction form. You very, very rarely are going to run this through a calculator. They're just going to have you set up these fractions and use these fractions. So get comfortable with the idea that they are fractions. The other thing to be aware of is if we change the point of reference, it's going to change our answer. If we ask about the sine of B, the sine of B is still opposite over hypotenuse. The hypotenuse is still the hypotenuse. Again, that hypotenuse is a consistent one. It's not going to change. Hypotenuse is still 5. But if we change the angle B, opposite B is 3. And the sine of angle A versus the sine of angle B, it's a different answer, even though they are both sine, because they have a different point of reference. All right. If you want to, I'm going to be pulling problems from practice text test number 6. I can't speak. So in your 10 test book, mine's orange, yours is blue, but it's on page 445 is where I'm drawing the practice problem from. If you don't want to open that up, that's fine. But we are told that the sine of A equals 3/5. And they ask us to find the tangent of A. They don't give us a whole lot of information beyond that. They don't give us a picture, they don't give us other information, just this is what we are working with. And so, for these, I want you to be able to recognize what's going on. The instant they tell us sine A, we've got a right triangle going on. The trig ratios are using right triangles. And so if we've got the sine of A, we've got a right triangle with an angle at A, and it's the sine, which is the opposite over the hypotenuse. So we know we've got the opposite, we've got the hypotenuse. Our opposite is 3. Our hypotenuse is 5. Again, I'm hammering home these 3, 4, 5 relationships because they do truly show up a lot. But if you didn't know the 3, 4, 5 relationship, you would be setting up a Pythagorean theorem that said a squared plus b squared equals c squared, and my a squared is 3 squared, and my c squared is my hypotenuse is 5 squared, and we'd be solving for the unknown side. And so if you don't know 3, 4, 5, you'd be trying to figure out, okay, what is this missing part of the triangle? And so again, knowing that 3, 4, 5 relationship saves you the time. So 25 minus 9 equals 16. Square root of 16, b equals 4. So again, they started with A, and they told us the sine of A was 3/5. We figured out the missing side. What pieces do we need in order to find tangent?
Opposite adjacent.
Yeah, TOA, tangent is opposite over adjacent, so we need the opposite over the adjacent. Well, we already had opposite over hypotenuse, so the opposite is still 3. That hasn't changed because we stayed with angle A. But the adjacent that we found is 4. And so the tangent is 3/4. Of the trig problems that I've seen on the ACT, this one is kind of the classic one. It's using the relationship, it's using a right triangle, set it up, and find a different trig relationship from the one we gave you based on the other parts of that triangle. So this is kind of the classic trig problem about the level of difficulty that you'll see. I'm gonna leave that part. Right. So here they've given us the picture, and again we have A, B, C as the corner points. They're fond of those. We have points. We have a distance of 6 and a question mark right here. And my bad drawing aside, they tell us that that's the right angle. So it says in triangle ABC shown, sine of C equals 2/3. And the length of AB is 6. That was already in the drawing, so not as necessary. What is the length in inches of AC? And again, they give us the question mark, so it's really easy to focus on what has this problem asked. So again, with the sine of C, here is our angle C. It's talking about the opposite across from C and the hypotenuse, the one that's the longest, the one that's across from the right angle. And so this equals the opposite over the hypotenuse. Our opposite is 6, and our hypotenuse is the thing we're looking for. You could see this as a proportion problem, a cross multiply problem, a change the base of a fraction problem. In order to get from 2 to 6, what are we multiplying by? 2 times something equals 6. Dig deep. It's back there in elementary somewhere. 2 times 3. And with equivalent fractions, we have to do the same thing. So 3 times 3 will be 9. And so our missing length is 9. If you prefer the cross multiply method, we get 3 times 6 equals 2 times unknown. 18 equals 2 times unknown. Divide both sides by 2. 9 equals that thing we're looking for. If you are a variable person, you can do X. I like question mark because it makes it blatantly obvious. This is the piece we're looking for. But the whole point is that these are called trigonometric ratios. They're about the proportion between the two sides, and it works for the same angle no matter how big the triangle is, or how small. Those are trig ratios. All right, another one. For an angle with the measure A, what looks like this alpha, the sine of alpha equals 40 over 41, and the tangent of alpha equals 40 over 9. And we are asked to find the cosine of alpha. Give it your best shot. This one I could do without drawing a triangle, but if you are feeling uncertain at all, I would highly encourage you to draw one for reference. here's our angle, here's our right angle. Hypotenuse is always the long diagonal across from the right angle. From angle alpha, this is our opposite, and this is our adjacent. If the sine of alpha is 40 over 41, sine is opposite over hypotenuse, we're going to have 40 over 41. For our tangent, it's opposite over adjacent. Again, our opposite is still 40, but our adjacent is 9, filling in the blanks. So for our cosine, we need adjacent over hypotenuse, still of alpha. Adjacent to alpha is 9, hypotenuse is 41. So again, for most of these problems, they will keep it in the fraction form. You just have to be able to work with the relationship. Questions? Again, I tell my students I want to be the opposite of a magician. I do not want to wave my hands and you go, how did she do that? All right. If you have opened up this book, I'm going to have you go to the very end of this test at number 56. It says, for the values of x where sine x, cosine x, and tangent x are all defined, they give us cosine x divided by tangent x sine x. And they're asking you to essentially simplify this ratio. This is a little bit beyond what you guys have usually done, but on page 4 we've got the trigonometry relationships, and there's this specific one that I think is the one that shows up the most, so I'm going to show you about it. And that says that tangent equals sine over cosine. If you look at this, sine is the opposite divided by the hypotenuse. And the cosine is the adjacent divided by the hypotenuse. And so, with fractions, equivalent fractions or equal fractions are any time we multiply the top and the bottom by the same thing. And so here, both of these are divided by h. We're just going to multiply times h over h, or hypotenuse over hypotenuse. If you were to multiply the top and the bottom by the same thing, this hypotenuse, h divided by h cancels, all we have left is opposite. H divided by h cancels, all we have is the adjacent. And so sine divided by cosine simplifies to tangent. Again, this one is a stretch goal. If you've got it, great. If you don't get it, the chances of it showing up are about 1 in 7. And so this is the stretch goal of trig. But back to this thing, tangent equals sine, I need to get myself more room. So we've got cosine on the top still, cosine of x. Tangent is sine of x divided by cosine x. And then this is times sine x. One of the biggest things you can do with fractions and this will come up in Algebra 2 a lot. And I think a lot of you said that you had done geometry, so you're taking Algebra 2 right now. This is going to be second semester Algebra 2 stuff, but I'm just showing it to you so that if it comes up. So we're going to multiply the top and the bottom by cosine. Cosine times cosine becomes cosine squared. Cosine times cosine here disappears, cancels out, eliminates. Sine x times sine x becomes sine squared. And so this is the simplification of this one. Again, if you weren't getting the previous trig stuff, I would practice that more. That one's always going to show up. This is the stretch goal if you're aiming for perfection. Add sine divided by cosine equals tangent to your arsenal of tools you can use. Final one is a case of don't be intimidated. I'm going to show you what I mean by that. This is a big, long word problem, and showing the camera, it's number 60 from a test. So it's the very last problem on an ACT test. And again, I will tell you, if you have not hit problem 60 before they say time's up, put down your pencil, you have taken the test wrong. Get to the end, or you have gotten too stuck on a problem because you never know until you try if you could have done that last problem. So it's got this picture, it's got a story problem with guy wires and poles and all of this stuff, but it says a hill makes an angle of 20 degrees with the horizontal. And again, they give us the picture. We've got 20 degrees. This is the hill. This is absolute flat. And a taut guy wire, AB, extends from the base of the hill, point A, to point B on a vertical pole. And again, they've given us the picture. Here's the guy wire. And there's a pole with point B. And they also have point A, and then point D down here. And they have given us point C at the bottom of the pole. All of this is contained in the picture. And again, they tell us that it's 60 feet and 25 feet above the pole. All of this is given information. And then they throw at us two equations. For a triangle with a side length A, B, and C that are opposite angles, angle A, B, and C, sine A over A equals sine B over B equals sine C over C. They've given us this formula, and they give us the formula that C squared equals A squared plus B squared minus 2AB cosine C. So they've given us all of this information, and they've given us all of these formulas. This is not a trigonometry problem per se. They've already given us the formulas. They've already given us information. You just have to be able to plug it in. And so finally, the question is, which of the following expressions represents the length in feet of the guy wire? So we know that this is 60. We know that this is 25. We're trying to figure out how long this piece is. And we know that this is a right angle We know this is 20 degrees. We're trying to figure out how long that side is. So, if this is 20 degrees, back to triangles add up to 180, what would this angle be? That's the first thing we need to know. You can start with the 180 for the whole triangle, subtract 90 for the right angle, subtract 20 for the other angle. This angle right here is going to be 70. That's our first piece of information that we need to know. Next, if this is 70, what is this angle? Remember, a straight line also makes 180 degrees. If part of it is 70, 180 minus 70 gives us the other piece, which is 110. So now we know that this angle is 110 degrees. We don't have anything to work with on these other two angles. We've got a right angle, we've got 20, but we don't have anything to work with the larger triangle as far as angles go. So, again, you'll work with this in Algebra 2. This one is called the law of sines. This one is the law of cosines. This one because it's using sine. This one's because it's using cosine. In order to work with this one, you need to have both a side length and the angle across from it. We've got 25, but we don't know this angle. We've got 60, but we don't know this angle. We've got 110, but we don't know this side. And so this one's not going to work. They just gave it to you for more extra information. We can't use that one. But this formula says if we're looking for a side, we need to know the other two sides, and we need to know the angle across from the side we're looking for. And so this is the formula we can use. And notice it says, which of the following expressions represent the length in feet? It's an expression. They're not looking for an answer. All we have to do is plug this information into this equation. And so c squared, if we're looking for just the length, it's going to equal the square root of everything else. So if we're looking for just c, we're going to square root all that other side. A squared and b squared are the two sides we know. We're going to have 60 squared plus 25 squared minus 2 times 60 times 25, and then cosine. Finally, the angle we know is 110. And that's the answer that you will put in there. So much of the ACT stuff is about the setup, not the solution. They want to know, this is what I plug into the equation. They don't care what the answer is. They care about the structure for finding it. And so if you can set this up enough to figure out, okay, this is the angle I've got, and then plug it into the equation that they gave you, they don't expect you to have that equation memorized. But if you can use it, again, it's problem 60 on a test. This is the stretch goal of trigonometry. Most of what you're going to see is the I've got the two sides, can I find the third one? So, this is what I want you to know. I want you to be able to find, okay, they gave me the sine, can I find the cosine? This is the limits of where it can go. That's the most difficult thing they're going to ask. All right. Taking a step back, we're going to work on circles for the second half of class. So, basic definition, a circle is the collection of all of the points that are the same distance from one center point. Things that we need to know. What's the distance from the center to the outside? Radius. And double that, the distance from edge to edge at the widest point is called the diameter. Most of what you will be working with is either circles, using that idea of radius and diameter in conjunction with triangles, or circumference and area. And we're going to mostly focus on circumference and area for the review today. So, we've got two formulas. Circumference, again, it's perimeter for a circle. And so if you need to make note of that, remind yourself that circumference is the distance around the circle. Area, more self-explanatory. Area is the total stuff inside of a circle. So, in general, I find that people are really good at memorizing these two formulas, and then they get self-doubting about which one is it that I need. They can remember the formulas, and they remember that it's got that pi in it, but then they start going, is that one circumference or is that one area? Is that one circumference or is that one area? So circumference is 2 pi times radius, or diameter times pi. You don't need both of them. You just have to pick which one is most comfortable to you. The thing that you need to be aware of more than anything else is that 2 radiuses makes 1 diameter. Because remember, radius is the distance from the center to the outside. Diameter is center to outside in both directions, so twice as long. The area is that same pi times radius squared. My key to remembering is that area is measured in squares. The formula that has radius squared in it is the one that is measuring area. And so if you see squared, oh yeah, measure in squares. That's area. This diameter times pi, that has to do with where pi comes from. Pi is the circumference of a circle divided by the diameter of the circle, gives us the ratio pi. And it is the same number for all circles. That's why it exists. The other thing to be aware of in the circle equations is that very frequently you're going to leave it in terms of pi. You probably were taught to use the approximation 3.14 for a lot of your earlier exposure to it, especially pre-geometry. They just use 3.14. For geometry, sometimes they leave it in terms of pi, sometimes you get it to a number approximation. For Algebra 2, they frequently leave it in terms of pi. For ACT, you're really frequently leaving it in terms of pi. A lot of your answers will just be number times pi. So get comfortable with leaving it there. Great, never mind. So I made all that emphasis about leaving it in terms of pi, but the first problem that I see, we're not. So this one gives us a circle on top with a diameter of 30, and it's 30 feet. It's a fairly large setup. And a circle below it with a diameter of 50. So here is our diagram they give us, and the story problem for it says that a track for a model railroad display is set up as two circles that are tangent to one another and have diameters of 50 feet and 30 feet, as shown below. The engine of the train travels at a constant rate of 75 feet per minute. Just to give us the details. To the nearest minute, how many minutes does it take the engine to go in a figure 8 pattern around the entire track exactly one time? So again, a figure 8 pattern, it's going to go here, going to go around this circle, switch, go around this circle, and it will have completed the entire track. So, in order to solve this, what do we need to know? Yes?
The perimeter of both circles.
Yeah, we've got to find the perimeter of both circles. We have both this one and this one. Remember, perimeter is the circumference. And since they gave it to us in diameter, this one's slightly easier to use. If you remember this formula, you would need to say, okay, my radius is 15, and then you end up with 2 times 15 and you get right back to that 30. So again, either formula works, but the more comfortable you are with both of them, it makes it a little bit easier. So we are going to have 30 pi, and down here we would have 50 pi. Add, subtract, multiply, or divide. How am I going to combine these two perimeters? Add. We just add them together. We have 30 and 50. We have a total of 80 pi is our total distance. But we need to get it out of pi because we're talking about feet per minute, so we need to get total feet. Because it says we're rounding to the nearest minute, it's not super critical to be exact. It's going to be a little bit forgiving. So you can either use the 3.14 or you can use the pi button of your calculator. Both are okay. So it's going to be something over 240. What did you get? 251. Okay, so 251 approximately. So if it needs to travel 251 feet and it goes 75 feet per minute, how do we find out how long it takes? Divide? Okay, what are we dividing by?
251 divided by 75.
Yes. If you can just see that, great. If you have trouble with rates of any type, per means divide. And so this is saying that 75 divided by 1 minute, so 75 feet divided by 1 minute, it's going to equal our 251 feet divided by what we're trying to figure out, minutes. And so, again, setting up the cross multiply, we end up with 251 because 251 times 1 is still 251, and then divide by 75. What do we get? Yes?
3.35 minutes.
So 3.35, and again, they asked us to round to the nearest minute. So what's our nearest minute?
3.
Just 3. And so our answer would be about 3 minutes. So we've got our circle perimeter in there. We also had a little bit of a rate review, which is good. Again, anytime you have per means divide. If you need to set up that proportion, do that. Yes?
What were we solving for on that?
So they had originally given us this track situation, and they gave us 75 feet per minute, and they asked how many minutes does it take to go all the way around the track.
Okay.
And so we found out the full length of the track was this 251. It would take 3.35 minutes to go all the way around, but to the nearest minute it takes about 3. Right. So this, again, after you take so many ACT tests, and one of the things that I did to prepare for teaching this was just take a pile of ACT tests so that I could get a sense for what kinds of problems they're asking and what they expect you to know. So this one is a very classic problem. You're given a circle and it's inscribed inside a square. And they tell you that the radius is 6. What's the area of the square? My first hint is that if you are doing anything with pi, you are making this problem too difficult. If our radius is 6, then our diameter, total distance across, is 12. And in the other direction, it's also 12. It's a square, it's a circle, it's the same in both directions. What's 12 times 12? We have 144 units squared. So, kind of a trick problem that they seem to be fond of. You do have to recognize that the radius is going to be the same as this length of the square, but you don't have to find the area of that circle at all. It's just, hey, here's a length, apply it to the square. Now, let's take it and make it into a circle problem. The area of the shaded region. And all they've got is that little corner. How would we set it up now? So conceptually, what you need to know is that in order to find this piece, you're going to take the square that we found, subtract the circle, would give us all 4 of these pieces, and then we divide by 4 in order to find one of those pieces. So we already found the square, being 144, and then we subtract out our circle, and again, area pi r squared, radius was 6, so 6 squared is 36 pi, and then divided by 4. Depending on the problem, sometimes they might have you calculate it out, but again, frequently they leave this in terms of pi, and so you just simplify that. 144 divided by 4 is equal to 38. 144 divided by 4, 38. And then minus 36 divided by 4 is 9 pi. And so they will frequently leave the answers in that form rather than getting a decimal approximation. But questions about the square minus circle divided by 4 idea, does that make sense? Get comfortable with finding the path to the answer, because half the time that's what they're going to ask about, more so than the number itself. They are really interested in the setup more than the answer. It boils down to, yeah, we know the answer. We want to see if you can show us how to get there. Right. Possibly our last problem until break. We'll see how fast this one goes. But this mixes our 2 topics. It's going to mix trigonometry and circle. And so we have radius of our circle is from point O to A, is perpendicular to AP, P being out here. The circle intersects OP at B. So we've got to draw in OP, and then it intersects at B. This is all given to us in the drawing, and we are told that this angle is 20 degrees. APO is 20 degrees. The length of AP is 12 centimeters. Which of the following is closest to the length in centimeters of BP? So we are looking for this right here. So again, we have trigonometric ratios going on because we are given an angle and a right triangle, and we're asked to find a length. In this problem, they say, note, sine of 20 is 0.342, cosine of 20 is 0.940, and tangent of 20 is 0.0643. In general, you don't need to use that, but they provide it because technically the ACT can be done without a calculator. And so you're not required to use that, but it's good to know. The other thing to be aware of is how many of you have dealt with something called radians? Okay, it's something that again comes at the end of Algebra 2, and it's a different unit of measurement for angles, kind of like the difference between meters and feet. It's a completely different system. And the one thing to be aware of is sometimes your calculator will get set into radians rather than degrees, and it will mess with everything. In general, if you haven't done anything with it yet, your calculator should be in the right setting. But if you ever want to check that it's working, they tell you that the sine of 20 equals 0.342. Go ahead and enter sine of 20 into your calculator. I would guess you were in radians. So if we look in mode, yep, see, radian degree. And we can change it to degrees. But in general, that's another reason to use the numbers they give you, just because it eliminates that chance of making a mistake. Anybody else have a number come up, it's like 9.9 something, rather than the sine of 20 equals 0.342. So again, it's a risk with the calculators. You can always use the numbers they give you, but for you, again, you'll want to go into mode and change it into degrees. And again, since you're not using it for school, just leave your calculator in degrees. Good thing to check. All right, so we are looking for this piece. So the side I circled, is it opposite, adjacent, or hypotenuse? The hypotenuse. So for this setup, this 12, is that adjacent or opposite? It's adjacent. So we've got adjacent, we've got hypotenuse. Can't spell today. And this one we're going to label opposite for the sake of it. And so we can say, well, if this is the adjacent and this is the hypotenuse, then the cosine of 20 equals 12 over this thing we're looking for. I'm going to call it H for hypotenuse. You can put cosine 20 into your calculator now if you want, or you can use the number they gave you, that the cosine of 20 is 0.94. Good point of reference. How do we get a variable out of a bottom of a fraction? Do you guys remember how to deal with that? The formal structured definition of what's going on is we're going to multiply both sides by h and then divide both sides by this 0.94. What happens is that we end up trading them. And so 12 over 0.94 equals that hypotenuse we're looking for. What do we get? Going to be close to 12, but just a little bit longer.
It's like 12.8.
Okay, 12.8 is great. So, really tempting to stop here and use this as our answer. But they specifically asked for BP, and so highlighting in this in color, that's only this piece of it. So if the whole thing is 12.8, how do we find just the pink piece? Well, we're going to have to take away the radius. And the good news is, back to this idea of circle, this is also the radius. And so we have to go back and solve for this side too. And so I'm going to use tangent because I like going back to the original length they gave us just to avoid confusion. So I'm going to say, okay, the tangent of 20 equals my opposite, I'm going to call it x, over my adjacent, which is 12. Tangent of 20, again, you can use the calculator, but you can also use the number they gave you. This is 0.364. Variable on the top of a fraction is easier. How do I solve for x? Times 12. So we're going to take 12 times 0.364. And what do we get? Three, a little bit more than 3. What do we get?
4.4.
Oh, never mind, that was off. That's why we do calculators. So this is 4.4. The whole thing is 12.8. This is 4.4. To find this piece, we take our 12.8 and subtract 4.4, and we get 8.4 left over. All right. So one of these pieces as an individual, solving for this side or this side, is something that you'll see fairly regularly. This particular setup with the circle and the extra piece makes this more of a challenge problem. But I would be prepared to solve for a side using the trigonometry pretty regularly. All right, go ahead, take a break.